Okay, good morning. So my name is Patrick Grimont. I am working at the European Space Agency in Frascati, close to Rome. And I'm working on the Copernicus ground segment. So in our group, we are dealing with the mission planning of the instruments, acquisition of the data, processing level 0, level 1, level 2, archiving, and distribution to the final users. So there's just some fact on the current status of the Copernicus ground segment. So the first satellite, SODL-1A, was launched in April 2014. And currently, so we are now 7 satellites flying. And the operation now, we are operating our satellites since more than 5.5 years. In terms of performances, we achieve good performances it's now, and we are behind the original target in terms of performances. So today, the Copernicus ground segment is processing systematically all the data that we archive. So we process level 0, level 1, and level 2 in systematic way. All the data are available to the users and are online. The data are free and open access. And in average now, we process up to 10 petabytes of data per year. So the 7 satellites that are flying are currently in routine operation. So in terms of mission, we have 4 missions. We have Sentinel-1, Sentinel-2, Sentinel-3, and Sentinel-5P. So here you can see in terms of operation. So in average, so we acquired every 10 minutes, we acquired data over our X-band station. We have archiving more than 50,000 orbits per year of data. And in terms of success rate, it's higher than 99.7%. You can see the trend in terms of archiving. So now we are currently in our archive for the 4 missions, more than 22 petabytes of data in our archive. That's for 1 copy, and all our data are duplicated. That means it's more than 45 petabytes of data in our Copernicus archive. In terms of flow, so you can see in systematic way. So each second we receive 3 gigabits from the satellites as raw data, and in output is more than 30 gigabits per second, and that's permanent flow. For the user's point of view, so you can see here in terms of statistics, so we have more than 20 million of products published to the users available. We have more than 265,000 users. Each week, we increase the number of users by more than 1,000. The access rate is also 99.7%. And in terms of volume, download to the users is almost 200 petabytes of data distributed to the users since the start of the operation. In terms of data ratio, so you can see in the middle, so for each mission, so for each product that we process, the Sentinel-1, for each product generated, we delivered 13 times. And you can see 5P is the more popular of the Sentinel mission. In terms of performances, so today more than 75% of the non-critical products are generated in less than 7 hours. So they're available to the users 7 hours after sensing. And for real-time products, for Sentinel-1 in particular, we achieved 2 hours for the delivery of the product. Each year, we generate a report on the Sentinel data access that is accessible online. So we'll generate in the next month the 2019 report. For the future, you can see on this graph, the plan in terms of satellite launch. So in 2022, we'll resume the launching of satellites. So as you know, for Sentinel-1, Sentinel-2, Sentinel-3, it is planned for each of these 3 missions to have up to 4 satellites. So Commission asked us that we shall have 3 satellites running in parallel as the maximum. Normally, the lifetime of the satellite is 10 years. That means in 2022, for Sentinel-1, we'll launch Sentinel-1C. And after 10 years of operation, so in 2024, we'll normally stop Sentinel-1A and launch Sentinel-1D. And that's the same for Sentinel-2, Sentinel-3. So here you can see at the end the evolution of the number of satellites flying for Copernicus. In terms of archive, so you can see the trend in terms of a cumulative archive. So today we are about more than 30 petabytes of data. And 2028 is more than 90 petabytes of data based on this number of satellites flying. Here, I just present the current Sentinel mission, but as you know, ESA has planned to have other missions, say for Copernicus, that will arrive in 2026. And this mission will really increase the number of satellites it will normally not yet completely confirmed with the Commission, but we should have more than 30 satellites flying in 2028, and the volume will be multiplied by 100 in terms of processing of data. So in terms of analysis of trends and risk, so as I said before, currently the operations are working well, so we have good success in our operation. And as discussed a lot this yesterday and today, so there is a big evolution in IT domain, in particular on cloud and open source. We want now to transform our ground segment to take benefit of this evolution of the IT and to make use of the public cloud services. So today we are currently transforming our ground segment, and we intend to put all our ground segment on the cloud, on public cloud. So that's today transformation we are currently running, and we expect to conclude this transformation by end of 2022. We need to maintain our system in order to give access to all our product to the users. So based on the trend in terms of volume of data coming to the system, we need to maintain our system and to evolve our system to allow this, that the user can access to all the data. Still, the volume growth of the archive is really too high to be sustainable, so we have to find a solution. So for now, we are archiving everything. So for now, we archive level 0, level 1, and level 2 data. By 2022, we will change this paradigm. So what we will start to do in 2022, we will stop to archive level 1 and level 2. And if the user wants to have a level 1, we'll reprocess from the level 0. So we'll implement on-demand processing. We'll also work on the processor. We want to adapt our processor in order to develop more flexible processor and to simplify the life of the users. So we'll allow from on-demand processing so the user can select the parameters he wants, and you can also create smaller data units. I will now give you a small presentation of how to optimize the data access and using the user behavior. So today, as I said, the data that we have so we have 10 petabytes of data per year. And the data access system is a data access system, keep 1 year of data online. That today is the paradigm we have in place. So if data is older than 1 year, we remove it from the archive. So if the user wants to get the data, we have to retrieve it from the long-term archive. So in terms of delay, it increases the delay for the users to access to the data. We want to analyze at the end how the user behaves. So you can see on this graph, the number of products, how it evolved since 2014. So you can see in the last year, we doubled the number of products, and the trend will continue in this way. So in 2017, we have 5 petabytes of data in the archive online, on the data access online, and now we have more than 15 petabytes of data. That means we need to reduce that, otherwise our data access will no more be sustainable. We try to analyze the user behavior. We want to check at the end the interest of the user from the date of the data. So what we can see on that, at the end, the users is very interested in fresh data. So they don't want to take the data that less than 2 days. The data that is older at the end, you can see that only there's some peak after 3 months and after 1 year, but most of the data takes the data immediately after they are available on the data access system. It's another way to present this user behavior. So you can see that after 30 days, all the products normally are retrieved by your users. For a product that is older than 2 months, only half the product are retrieved. And for products that is older than 10 months, only 20% of the product are used. So as said before, today, the data access system, the ESA data access system is on cloud. So today we need to have what you put, because we keep 1 year of data online, we have 10 petabytes of data on the cloud to put our data so the user can access directly the data from the data access system. So we have a rolling window of 1 year to keep data online. Then if the data is not online, the data retrieved from the long-term archive, we have this cache window where we keep the data after a retrieval from the long-term archive. The third definition is average storage size. It's the average number of products that we store online. And the last definition, what we call user satisfaction. For that, we want to measure at the end is the number of products requested that are online versus what is offline. So this gives us at the end user satisfaction. So analyzing the current user behavior, we can see that the first line on this table is where we are today. So we have 1 year of data online, data access system. We have a cache window for retrieval for long-term archive of 3 days. And we have a user satisfaction of 99.38%. Now, if you look to that table, if you go to the fourth line, for example, if you reduce the rolling archive to 200 days, we can see that we just decrease satisfaction by 3%. And doing that, we can reduce our cost of operation by half. So reducing 3% user satisfaction reduces the cost by 50%. So is it worth to do that? It's acceptable for the users that at the end we do that. So what we want to see at the end, maybe we need to change our requirements, not that we keep 1 year of data, but want to, at the end, to have the best user satisfaction as possible. And maybe you can use machine learning in order to adapt our archives, our system according to the user strategy. So what we have done at the end, using machine learning, we have put on the map, it's a representation of all the requests made by the users. So you can see on this map, each square is inversely proportional to the number of requests made by the user on the particular zone. So using this map, using a machine learning system, we want at the end to generate as an output a download pattern identification. From that output, then we can fine-tune our rolling strategy. It's a way to increase the user satisfaction. To have an automatic way at the end to optimize the size of the data online archive. As a conclusion, so as said before, so Copernicus operation is generating large data flow. So we want to see at the end, we are currently working on machine learning, and we check 2 particular ways to optimize operation and how to use machine learning. The first part is error detection. So we want to see how to use machine learning and how to optimize our operation. So we can see directly if we are missing data in our chain, so we can automatically generate recovery. So the second thing is this dynamic adaptation of the resource computation, what I mentioned before for intelligent cache strategy. So the last part still for the machine learning is how we can, the Copernicus core operation can better support machine learning so for the users. And for that, we have different initiatives. So the first one, we are working on the product definition, and we want to allow large blocks of data extraction and to generate subsetting for the users. We want to work on new data format, what we just discussed before. So to see at the end what's the best format for the users to access, and in particular for on-demand production. So now that we only keep level 0, the users will be able to generate level 1, level 2 on demand. So new formats are important for that. And this also will reduce the volume of transfer of data. And the last point is traceability, what was discussed this morning. So the first things that each time a product is generated on the Copernicus ground segment, the producer will generate a trace. And as part of this trace, there will be a checksum to identify and to verify the integrity of the product. And we will keep also some information on the context of the production. Then doing that, if the users take a product, he can verify the integrity of his product and how the product has been generated. He can also know what is the latest version of the product. That's the end of my presentation.
All right, good morning, everyone. I'm Joe Flasher. I'm the Open Geospatial Data Lead at Amazon Web Services. If you're not familiar with AWS, we are an infrastructure company. I once learned my lesson because I gave, I thought, what was a fantastic presentation. It was like 40 minutes long. And at the end, somebody came up to me and they're like, so you like deliver my packages? And I was like, it's sorta. And they're like, and you sell people computers? And I was like, I mean, okay, you're getting further away. And she was like, and you make money doing this? And I was like, yeah, we're doing okay. So if you don't know who AWS is, we provide access to compute infrastructure. So this is selling us a bit short, but you can think of it as a lot of compute power, a lot of database, a lot of storage, and then we have a whole lot of other services, some of which I'll talk about in a bit. So I wanted to sort of, I wanted to share with you what Hamed asked me as a way to frame some of my comments. What he wrote to me was, what resources is AWS developing and advancing to enable ML applications and make it easier for the broader community to use them? So AWS is a big company. If you ask different people within the company, you will get different answers. I'm not an ML person. I don't work on any of our ML teams. I am ML adjacent, I would say. But I focus more on the data side. So I'll sort of cover everything that I think about, but just full warning, if you talk to other people in the company, they'd sort of give you, they'd go in depth in other parts. So the way that I would answer this question is by thinking about the data that we make available and we help customers make available, the tools that we make available, and then the examples that we make available. So you'll see when I get to it, but this isn't examples of people doing cool stuff. What I mean by this is how we're helping people get examples, good examples out there to the world. And I want to sort of explicitly call out, in case I don't later, most of what I'm going to be talking about is how we're helping our customers do work. A lot of this is not us ourselves doing work. I'll talk a little bit about some of the tools that we have, and that's like our services and tools that we're putting out there. But a lot of this is sort of leading by example through our customers and helping our customers get things done that they're trying to get done. So in the data piece, if any of you have seen me talk before, I hope I mentioned the Open Data Program and the Public Dataset Program. So we work with customers to get data publicly available in the cloud. We have something called the Public Dataset Program. If you're ever looking for data publicly available on AWS, you can go to the Registry of Open Data on AWS. There will list a whole bunch of different data sets there. I focus on geospatial. About a third of those data sets are geospatial. That means a lot of them aren't. We also have a lot of genomics data, things that are actually like natural language processing things, which may be of interest to this group. But the point is not all of it's geospatial. We've got data sets from all over the place. With one or two exceptions, all of these data are coming from other people and not us ourselves. We don't own the accounts that this data sits in. It's all owned and managed by customers. And in most cases, well, I should say a lot of you in the room are those customers putting data up there, right? And if I sort of change this to not being data that's in our public data set program, which is like capital P, capital D, capital P, that's like a thing. And I just say data that is publicly available on AWS, which is what you more care about, right? This is data that's publicly made available, generally in an object store, which is what's been talked about a lot here. A lot of you in the room are already doing that. So Pete will be talking from USGS. They have initiatives along the way there. I think this may have come up the other day with some of the NASA conversations. Alex is from Geoscience Australia. I don't know if they'll mention it, but they're doing stuff along that line. Andy from Facebook, they have data that's up there. So a lot of you in the room are already making your data available in the cloud, right? And we're very fortunate that a lot of that is on AWS. So I don't want to go too much into depth into the data piece because it's already been covered a lot. But I see our piece that we're adding here is that we're very fortunate in that we have a lot of you and others as customers who we can work with to figure out best practices for making this data available, right? As a pretty cool example, so the presentation from the Copernicus program, we just, through a customer, made Sentinel-5P data available, but they came to us and specifically made it available through the public dataset program because they made it available in cloud-optimized GeoTIFF along with stack metadata, which is something that currently doesn't exist, right? So it's a cool way that we can help the community get the data out there in new formats and show exemplar data sets in new ways to help try and bring everyone along. So just on the tools piece, we have a whole lot of ML tools. I'm not going to go into depth in any of these. You can find tons of documentation and very beautiful websites if you want more information. But I think we generally take a three-tier approach. And I think this is where it's important to realize, again, that we're an infrastructure company. And so the last thing that we want to do is to lock anyone into certain tool sets or certain frameworks. And so we try to support everything because our customers want to use everything. So at the base level, if you are sort of one of the, I mean, and I think a lot of you in the room are, of the people who want to touch these sorts of tools and frameworks yourself, you can run all these things on AWS and various of our services. And one of the cool things that I like working about AWS is that we often do things like we saw a lot of customers that were buying machines with big GPUs on them, but then they weren't actually using those GPUs to full capacity. So we basically announced a service. It's called Elastic Inference over there, which lets you just pay for the amount of GPU that you use, right? So you don't need to get a big GPU instance and then not use any of it, right? We only want you to pay for what you use. That's a general cloud principle. The next level up you'll start to see things. SageMaker is a big thing. It's basically our overarching name for a whole bunch of these sort of managed services. If you're looking to train a model and then deploy it into production, and it'll automatically do model drift detection, which I knew came up earlier. It'll warn you if like you start to see too much drift. We launched a whole bunch of stuff around this recently in December at our big user conference. But there's like one-click Jupyter notebooks now, and it was actually really cool. And like I said, I'm not an ML person. I just put in a whole bunch of data that I thought would be appropriate for ML data. It was air quality data around the world, and I just said like, go train me a model. I kind of don't even know what this means. I feel like this is turning into a therapy session. I'm sorry, but I just said like, go train me a model. But then it didn't just give me a number at the end of the day. It did do that, but what it also did was it gave me a set of notebooks that told me everything that it had done to do that on my behalf. I looked at the first notebook and I was like, I don't know what this means. I looked at the second notebook, which was telling me things about the data. It was much more easier to follow. But the point is there that it's trying to help you learn what it's doing on your behalf. I'm going to talk about one more service from there, which is relevant for this audience in a second. But then we have the highest level, which we would call services, AI services. And these are things like if you don't care what's going on underneath the hood, like if you're just trying to get like text to speech, speech to text, like you want to get, what is it, like, there's a word for it, but like the emotion out of a social media post or something, right? We have services that'll do that for you, right? Just send us the content, thank you. Send us the content and we will we will run our pre-trained models and give you the answers. So there's all sorts of different entry points for the various services. I put this up there because one of your logos are on here. So I will wait 5 seconds to see if anyone can find the logo. No, you're like, what do you, I mean, what do you, I don't know how closely you affiliate with Tinder, but the NASA logo is up there. It's NASA JPL, so I don't know if it fully counts, but there is the NASA logo is up there. So the one thing I want to hit real quick is SageMaker Ground Truth, which is pretty cool. And I think sort of points out something cool that we can do with the number of services that we have. We already had a service called Mechanical Turk through which we let people like have an API for humans, right? You can say, I want this task done, and humans can actually do that task. We also have, I just mentioned, SageMaker, which is a machine learning framework. And so what SageMaker Ground Truth did is say like, I will jump to this piece. It said, give us your data. We will try to run our model on it based on what we know. We'll help you generate labels on that data. And if we need to generate more labels on that data to help you get to the accuracy that you want, we will let you define tasks so that you can use the Mechanical Turk network to have people label that data for you, right? So you can use the full Mechanical Turk network. I would not consider these people to be trained labelers, but you can also use the same framework with your own private crowd of people, right? So if you do have labelers that you're using, you can say, I want to use the same framework and use just these people that I trust. But it gives you like an overlay here, so you can do object labels, pixel labeling, semantic labeling, and then it will feed right back into the system and it'll start training your model again. And then if your model still hasn't reached the accuracy, it gives you more options for how to get more labels. And it'll help you figure out, and I don't have much detail on this, but I'll help you figure out how many labels you need to get to the accuracy that you're looking for. And then in the examples piece, we're a part of SpaceNet. SpaceNet's already been touched here a couple times, so I won't say too much here. But what I do want to say is one of the reasons why we find SpaceNet so valuable is because their focus is on making baseline models to help people understand what can be done, and then making sure that the algorithms that win the competitions are all open source to, again, help people understand what can be done, right? So they're not taking anything proprietary for themselves. They're trying to help the field as a whole learn from each other, right? Which is one of the things that we try to do as well. So we try to facilitate getting these best practices out there. Something I wanted to say earlier, but I didn't get to say, is back in the community piece when I was talking about the customers, it was mentioned before, but we just signed a NASA Space Act agreement. So we are actively looking for people to propose cool things that they want to do with the cloud and with any of the NASA data sets or tools. So if you have any ideas of what you would like to see us experiment with, please find me, find Rahul, Elizabeth, and we can talk to you. And I think that's it. Thank you.
Thanks, Ahmed, and good morning, everybody. So my name's Alex Leith. I work at Digital Earth Australia as a leader of a small technical team. I'm going to talk a little bit today about Digital Earth Australia, another project that we have, Digital Earth Africa, and give you some case studies on what we do and relate that a little bit into machine learning. So a brief history of Digital Earth Australia. We have a relationship with the USGS going back quite a long time. We were one of the downlink stations for the early satellites. Those satellites didn't have a lot of storage on them, so they had to push the data down as they flew around, and Australia is a long way away from the US, and so they pushed it to us. Now we stored that in Canberra in an archive on big old tapes. I've seen one of these. These are giant cassette tapes like this. They're not very easy to be getting data off. There was a project called Unlocking the Landsat Archive Project where those tapes were digitized. The data was stored on the NCI, which is our national compute infrastructure, a large supercomputer. There's a bit of software called the Australian Geoscience Data Cube written to facilitate getting that data out of the NetCDFs that were used on there. A little later, that software was updated and quite creatively renamed to the AGDC V2, and that enabled working with different coordinate reference systems and different data storage formats. Later, that was called the Open Data Cube, and that brings us up to about where we are today, where Digital Earth Australia is empowered to make a whole bunch of Earth observation data available and accessible to people across Australia through government, industry, and wider. So part of what we try and do is this, which is get raw data and turn it into information. So this is the output of one of our algorithms, which is called the Water Observations from Space. And it's a reasonably simple decision tree. I'm going to show you the actual decision tree later. And so this is kind of machine learning, but it's kind of old school machine learning. And I guess what we do in Geoscience Australia is we tend to be using kind of human understandable machine learning models. So it's more remote sensing classification than what we sort of call machine learning in this kind of discussion. And I guess what I'd like to sort of take away from this meeting is that we'd like to learn a bit more about doing these magical black box kind of throw all the data out at machine learning and try and transition to that. But doing that means getting the people that like to run algorithms like this and understand what they're actually doing and making them comfortable with doing the kind of magical stuff that's done. So when we talk about data, we talk about analysis ready data, and I want to throw this slide up there. Hopefully quite a few of you folks are aware of this idea, the importance of analysis ready data. But on the left, we have the USGS level 0 data, and we've run a modified normalized difference wetness index on that. And on the right, we have the exact same scene with level 2 or analysis ready data. And what you can see with exactly the same scale on both of those, that you know, it's night and day. So my point is that you can't do meaningful analysis on level 1 data. You need to have quality analysis ready data, which is where having the global availability of USGS's data at some time short in the future of level 2 data is going to be really fantastic. So the old way that we do things in Digital Earth Australia is that we actually got level 0 data off the USGS. We process that to level 1, then process that to level 2, and then we convert it into a local Australian projection, an Australian Albers, and stack it up into NetCDF files, put them on a supercomputer, and then nobody can get at them except for us. We can do analysis on it. It's quite convenient for us, but not for many other people. What we're moving more towards now is getting those legacy data formats that we have, converting them to cloud optimized GeoTIFFs and putting some of that up onto S3 or an alternative object store. What that means is that anybody can get at them. They're reachable through a public HTTP request, and it's really convenient and useful. So the way that we interact with this data is using the Open Data Cube, and I do want to talk about this a little bit. So this is a technical architecture, I guess, of the Open Data Cube. In essence, it's a Python library. It's a Python library with a Postgres database, which is an index of those files that we store, either NetCDF files on a file system or data on an object store. Really, we support reading data that's stored in almost any format that GDAL, raster.io can read. And then once you've got that, we use tools up in Python land to be able to go and write a query saying, with this lat long bounding box over this time space, I'd like some data, please. and it returns you an X-array. That X-array, for those that like the Pangeo kind of stuff, is all Dask aware and everything. So you can use Dask and all of those kind of fancy, fantastic tools natively with the Open Data Cube. So as I said, we work in Australia, and so this is a cloud-free, what we call a geomedian, which is a bit more fancy than just kind of getting a cloud-free image or a mean. It actually gets the median pixel, so it's a median observation, so all of the bands are captured at the same time. That's apparently quite a difficult computation, but it's important to be able to do that. And we do the same thing in Africa. So this one's done on a supercomputer, probably cost millions of dollars to get put there and actually run the thing. This one's done on AWS using data stored on S3 and cost us $140 and a couple of days of compute time. So we build a few tools sitting on top of our data. We have an architecture that we're leaning towards now where we store the data on S3 as cloud optimized GeoTIFFs, and that is public facing, so you can come in and directly get the data. But we also have a range of opinionated services that sit on top of that. One of those is the Jupyter Hub environment. We call it the sandbox. So you can land in the sandbox, the Digital Earth Australia sandbox, and start interacting with some of our code examples to learn the Open Data Cube, or analyses to learn about remote sensing, or some real world case studies to kind of see what we do and how we do things. This is a really brief example of one of these case studies, which is an example of looking at a mine site that's being rehabilitated. In addition to exploring the data in a data science sense, we also do have a visualization of where there is available data using a web map. And we have interactive OGC web services cranking out real-time visualizations from these things. This here is an example of the water observations from space, and it's an annual summary of those, where the blue areas are those areas that are wet all the time, and the red areas are wet some of the time. So it may be flooding and those kind of things. These web services, this is an image I captured just a couple of days ago. So we have data flowing in from Copernicus, for example, in a near real-time process. And so that's available within our web mapping within a few hours of it being available from ESA. Finally, I want to talk to you about a case study in reasonably big data processing. Every time I think I'm working with big data, I hear about someone else using far larger data, and so everything's just reasonably big, right? So this was a process we ran at the end of last year to run our fractional cover or fractional land cover process on Sentinel-2 data. We did this on AWS. So there's 300,000 Sentinel-2 granules. Each one's around about 1 gigabyte. So that's about 300 terabytes of data. Each job takes 10 minutes to run. We ran this process in 3 days in a auto-scaling cluster managed by Kubernetes. We ran it with the 3,500 containers. 400 spot EC2 instances were ordered and 40 terabytes of data were generated. This was managed by me, the naive leader, like pushing around, poking around Kubernetes, deploying little things. And it's kind of an illustration of being able to do some pretty big work with a pretty small, tight team, which I think is pretty cool. This is a graph showing us using 1,500 CPUs and 2.7 terabytes. It takes quite a long to load this graphics, but it's pretty cool. This is what one job looks like. So we have a big queue, an SQS queue, an AWS thing, basically a queue of jobs, and we stick jobs on there, and a Docker container runs, pulls a job off, does it, throws it away, starts again. So you can kind of see it picking up jobs and throwing them away. Having a profile like this means we can constrain our memory and CPU requirements, and then we can pack jobs onto machines really efficiently. So we end up using those 400 instances quite well. And something that I think is interesting is this graph. So this is a graph. The later part here is about when I was running all of this. What it shows is that we really didn't impact the spot price using 400 instances in the Sydney region on AWS. So I'm interested to run an experiment, Joe, and see if we can actually make that spot price go up. I'm not sure how many machines you'd have to order, but we thought that it'd start getting more costly in Sydney with this, but that was a bit naive. So finally, bringing this back around to machine learning, this is the decision tree that we use for our WAFS algorithm. And my point is really that there's a human readable aspect to this piece of machine learning. And as I said, I think this is important for us in terms of being able to justify the algorithms that we use and the information that we're generating so that we can hand it over to people and say we understand it. But I wonder if it's, there's soon coming a point where we can get these more black box algorithms I talked about and deliver a product that is an improvement on this, and we're comfortable that we don't have to understand how it came to be. Anyhow, why are we doing all of this? So Digital Earth Australia, we support government users and uses. We have recently received ongoing funding to do this work and support industry, and so we're running small grants programs and such to sort of enable industry. We're running Digital Earth Africa as well, looking to do the same thing, repeating the same kind of architecture and structure over there. And I think the hard part over there is the capacity development, finding the local people on the ground and getting this stuff happening with them. So I'm out of time, but thank you very much for listening, and please get in touch and have a chat to me if you want to know any more. Thanks.
Thank you, Hamed. I think the last few talks have set a nice foundation for what I'm going to cover here. I'll get into some machine learning that we've been developing for the Landsat archive, and hopefully, beyond that. So this is an artist rendition of Landsat 8. We like to show our satellites as much as possible, since ESA, NASA, NOAA have all kinds of satellite missions, and Landsat's our only mission, so we're quite proud of it. This will be a Landsat 9 will be a copy of 8. Landsat 9 will hopefully launch in a year, and so we're looking at Landsat 9, knock on wood. Okay, so Landsat data continuity goes back to 1972. Landsat's probably one of the more familiar sensors out there because of this long legacy. Landsat 7 and 8 are currently operating. Landsat 7 is expected to run out of fuel by 2020, 2021, at which time Landsat 9 will take its place. And then Landsat 10 is currently on the drawing board, hopefully a mid-2020s launch. And even though 9 will be a copy of 8 in terms of parameters, resolution and band passes, 10 will likely look quite a bit different. It's likely it'll have better spatial resolution, more spectral bands, but none of that's been determined. So it's highly likely that will go in that direction. Of course, as many of you know, all this data going back to 1972 has been meticulously calibrated, which is what kind of unleashes the value of the archive, right? It was unleashed for access in 2008. USGS adopted the free and open data policy in 2008, and the floodgates opened, created a new market, so to speak, for this moderate resolution type of data, and many agencies have followed suit with that model. Hope it continues. So here's, Alex talked about analysis-ready data. Here's the Landsat analysis-ready data. You just saw the new tiling system, and you can see how that works, right? As the sensors overpass, you have drift in the orbits, but the tile is fixed, so the upper left is always going to be in the upper left. ESA is using a similar kind of tiling approach with Copernicus data. And the bottom line is to facilitate time series, right? So facilitate stacking, and Alex showed this similar concept, where we're using an Albers conic projection for the US, and this is only available for the US. And hopefully people like Alex and others will continue prodding us to go global with this product. And I know there is a huge demand for global analysis-ready data for Landsat and other similar products. Where the Europeans use UTM for their projection because it's they're going global with it. This is just, again, it's just the US product for now, and it's Albers, but hopefully global is not far away. So what do we do with this analysis-ready data? So here you see a couple of, these are airborne scenes. These are not Landsat scenes. But that yellow box represents the size of a Landsat pixel, okay, superimposed, a 30-meter pixel there. That graph on the bottom, you see time on the x-axis and pixel intensity on the y-axis. So back in the day, if you wanted to do change detection and you didn't have a lot of data, or you couldn't afford a lot of data, you had maybe pairs here and there. And here, let's look at this Landsat pixel and plot it. Its intensity versus time. You've got this scene on the left, 1995, scene on the right, June of 2010. And you would do a threshold on their intensities and determine, is this change, right? Fairly simple, straightforward methods. But today, of course, we've got all the observations available in time throughout the ARCA. This goes back to 1984, which is Landsat 4. And more compute to drive much more sophisticated ways of doing change detection over time series analysis in effect, right? So fitting a harmonic regression model as such is a much more robust way of determining, was there change, between these two particular pixels. And so, in fact, a harmonic fit on the left is associated with deciduous forest, and on the right with low density residential. So there's obviously change going on in both of these fits. There's seasonal change, right? And that's what this harmonic is capturing. The peak of these sinusoidal waves is roughly the peak of the growing season. The troughs are kind of the dead of winter. And so you obviously have seasonal or phenological change going on, but you don't have class cover type change going on, except at where it changes from green to red. But a difference in the amplitude of the harmonic, ergo a change in cover type. And that's the kind of change you want to capture, right? You can see the math there at the bottom. So what actually serves as training data for associating a particular cover type with a kind of a spectral temporal trajectory are the coefficients, right? And you can see in the math in the bottom right, they're coefficients with the simple harmonic model that can be used as training coefficients for this particular harmonic fit, okay? Show another example of that. Here you see pre-fire, year fire occurred, and post-fire. You see the baseline in blue, and then the year the fire occurred, you see the break in that harmonic pattern, and then you see this linear trend for regrowth over time, right? And again, capturing the seasonality, capturing the change in cover type, if you will. Here you're seeing another example of this, but kind of a little more explicit. You see the actual Landsat scenes that from which the observations were derived. So what we're seeing at the bottom there, again, this is just for a single pixel's worth of information. This is done for every pixel. And that plot you're seeing, again, that's that harmonic fit, right? I forgot to mention it was called continuous change detection and classification. You can see Landsat 7 and 8, changing over the years. That yellow arrow is pointing at the pixel that's being represented in this plot. Okay, on the right, you can see another product, which is the time since last change. So the lighter the color, the more recent the change, and darker, the older the change, going down to black. Now you can see these yellow lines occurring here. One looks like before 1990, and then, so that's where you had a change of cover type or a disruptive change going on, right? Okay. Here's the second half of, so we just looked at continuous change detection, that's the first part of it, and then the classification part, which is, again, taking those harmonic coefficients, training on those, and tying those to a particular cover type. And then as it changes over, and you can see, now this is a fairly small set of classes here, and that's what we're going with the initial LC map. You can see on the right what that means, land change monitoring system projection. So green is forest, and you can see this is going at the last graphic had. This is in central California in the Sierra Mountains, and obviously fire is a problem there, and so a lot of this changeover is, when you see it, big massive changeover that is due to fire, going from forest to grasslands, for example. So this kind of product will become available going back to 1985, this land change monitoring system projection. So this kind of class product that'll be available at a frequency of 1 per year, I think starting at July 1st every year, will be available for the general public. Again, over the US for now, and it's completely dependent on ARD, right? It needs that meticulously calibrated data through time to do its thing. So where do we go next? Sensor harmonization, it's been spoken of quite a bit the last couple of days. These are the spectral band passes for Landsat 8, Landsat 7 are similar to this. And these are the band passes for Sentinel-2, right? Fairly similar, they're Landsat-like by design. They were originally designed to be Landsat-like, so you could create a quasi-constellation out of the Sentinels and the Landsats. And together you can get a revisit of roughly down to 2 to 3 days, depending on the orbits. We challenged our Landsat science team to try to do more with the commercial sat instruments that are being put up, Planet and others. They're in this part of the spectrum. Of course, radiometry isn't necessarily at the same level of quality as Sentinel or Landsat per se, but it's a different mission set, right? It's more revisit, more GST, or better GST. How can that augment what we're doing with the Landsat Sentinel constellation? So fairly ambitious goals, but the point is more observation. So HLS, or Harmonized Landsat 8 Sentinel 2, was talked about a couple times. Got this graphic from Jeff Masick at NASA. You can see these curves at the bottom. The red one is alfalfa fields. You probably can't see it, but you've got some, the plus sign, Landsat 8 observations. The diamonds are Sentinel 2 observations. So the whole point of harmonizing is to get more observations so that these harmonic-like fits can be more robust. So in this case, you can see those downward spikes reflect mowing events of these alfalfa fields, which may not have been captured if you only were using one sensor's worth of observations. That's the point. Okay, ML trends that I think a lot of media hype is pushing this perception right now, that neural networks, back in the day in the 80s and 90s when I studied them, and they were a bad word compared to the non-neural network-based methods, they weren't performing at nearly the same level. And it's only in recent years, I say maybe the last 10 years, the onset of big compute and GPUs in particular, that these deep learning neural nets have surpassed a lot of the more conventional methods, but by no means has that been clearly demonstrated for Earth observation data, right? The big application areas for deep learning neural nets that the cloud vendors are now moving into this space are obviously the computer vision, kind of the facial recognition and traffic and automobiles and that kind of thing, and voice recognition, right? Those are the two big areas. So it's, I'm heartened to see these kinds of workshops being put together so we can explore, do deep learning neural nets have a place for Earth observations? We need to determine that. We need to discern that. I was speaking with Lyndon last night about, so the methods I didn't go into what we're using for this land change monitoring product that will be coming out are random forest, started off with random forest and moved over to XGBoost decision trees. Not deep learning. Okay, we're not using deep learning as of yet. I think a lot of our research team hasn't really bought into these are going to be worth the extra 1 or 2% of accuracy you might get out of it at much more expense in training, right? So we're still making that, going through that discernment process. We'll see where it goes. Real briefly, so yeah, I'm out of time. Ryan and Pierre talked about this. So the possibility of hybrid methods, machine learning with physical models. So level 2 data versus level 1. Alex talked about this, the atmospheric correction. So here's another area that we might be able to leverage machine learning for what we do, going from level 1, top of atmosphere, to level 2, surface reflectance, and with cloud detection. I'll end on this slide here. This is ultimately what the decision makers want, to predict the future, right? So this is an example, and this is a physical model. It's not based on machine learning in any way. But this is a physical model that forecasts out or makes an assumption on the depletion rate of the Ogallala aquifer. What you see in purple are cotton crops, and which are very dependent on irrigation from the aquifer. As that declines, the aquifer, then those crops will have to be converted into dryland wheat or other crop types that are less dependent on irrigation. This is the kind of information decision makers need to get. So this is a projection scenario. You can come up with all kinds of scenarios. But to the degree that we understand how things change in the past, will make the ability to do this more robust. And I'll end on that note. Thanks.
Hi, everybody. I'm Benjamin Goldenberg. I work at Planet, managing a group that works on services, software, tooling for training our machine learning models, deploying those models, and managing the associated data sets. And I come more from a software engineering background and I've only been in Earth observation, remote sensing world the past few years. So briefly discuss our imagery. So we're focused on imagery from our Dove constellation. We build, launch, operate several different satellite constellations. The Doves are small satellites that sample about 4 meters per pixel in 4 bands, red, green, blue, and near infrared. And the work in this presentation was largely done with the Dove Classic and some of our recent Dove R satellites. I wanted to mention our upcoming Super Dove satellites that are number of these in orbit, and over the course of 2020, we'll be starting to produce 8-band products. And we specifically chose these 8 bands to be radiometrically consistent with Sentinel-2 to enable interoperability. And at Planet, we're hugely supportive of the public data sets, and we really view our data as a complement to the public data, and are really seeking to harmonize it and bring it to the calibration level that was just discussed. So these satellites have been deployed into a sun-synchronous polar orbit, so we get daily revisit rates of most of the globe to give us this incredibly rich data set to develop analytic applications. So I'm going to talk about one of those that we've built in the last year. And that is a global map of roads and buildings. In this map here, you see all the roads in green and buildings in red. And we've done this at our native resolution of about 4 meters per pixel. So it's not, roads and buildings aren't usually talked about as land classes, but I think they really are, just at a different resolution than some of the coarser classes we've been talking about. There was a lot of discussion yesterday about how to build a taxonomy for land classification. And we've settled on something really simple. To call it a building, it's something you can stand under. It's something you can drive over, we call it a road. Well, this sounds pretty simplistic, maybe naive. This really helps ground our labeling conversations, both with the people we're asking to do labeling, with customers down the line that we're trying to explain the product to, as well as the engineers. And I really think if we're going to try to build collaborative data sets, we really need to come up with simple definitions that can be understood by a wide variety of people with different backgrounds. So we don't get lost in these decisions of, is a yurt or a semi-open building count as a building? You can stand under a yurt, it's a building. Is a gravel road a road? You can drive on it, it's a road. So what can we do with this? In this case, zoomed in on a location in the Amazon where we've masked road pixels in yellow and buildings in this light red. You probably are immediately drawn to deforestation activities, these broad land cover classifications. But before that even happens, we can predict where these deforestation activities might happen by the development of roads that have been masked on the left side of this image. And this is something that we've really only been able to do by leveraging our higher resolution data. These broader land classification changes you can almost certainly see in Landsat Sentinel, but it'd be much more difficult to see the road classifications. Now, have we done this? Like probably lots of people in this room, we've used a standard neural network architecture called a UNet. This is fed the input imagery on the left side, learns a higher level representation, and produces a segmentation map in the same shape as the input raster, where now each band, instead of being a spectral band, is a semantic band. Roads might be the first band, buildings might be the second band. And we've done this hundreds and hundreds of times to get to a model that works as well as it does. So I wanted to talk a little bit about our learnings and tools for creating those models. This is a slogan I like to borrow from the DevOps world. That's to treat models like cattle, not pets. So we don't name models colloquially by referring to the model so-and-so trained last week on this data set they had. We give it an ID, we give it a serial number. And this is minted by a computer. It's not something a human comes up with. We do the same thing with data sets. And if we have multiple versions of a data set, maybe a smaller one for prototyping, then we give that also a data set ID. And this really makes conversations unambiguous. We know exactly what data set was used to evaluate exactly what model and what the metrics that came out of it were. And this is the pipeline we've built. And as I alluded to earlier, we've been really explicit about what's done in the geospatial domain and what's done in the modeling domain. So in the geospatial domain, we maintain catalogs of imagery that are stored in cloud storage, tracked in a Postgres database, as well as the associated labels that are served through stack-style APIs. And then we transform that data to the pixel domain, the modeling domain, where we feed it into standard deep learning frameworks like TensorFlow and Keras, and we train those models in Docker containers on Kubernetes. And then finally, we get this TensorFlow saved model that is this portable encapsulated object we can run on our compute clusters. Not only that, but we do it in reverse too. When we evaluate a model on a test data set, we produce another data set that's a set of predictions. We push it back to the data set store in the geospatial domain. And then when we compute performance metrics, you can just think of this as sort of a diff between two data sets. And it doesn't matter whether those data sets were produced by machines or produced by humans, we can still produce the precision and the recall of it. And finally, I wanted to talk about our work stitching this all together into a change detection product. So we've trained this model that appears to be this highly accurate segmentation model, and on individual results, it looks great. The performance metrics, the precision recall generally look pretty good. But when we run it over 18 months, we get lots of noise for reasons I'm sure you all can guess. Clouds, changes in sun angle, sensitivities in the model that we didn't mean to model. And we get lots of this little flicker you can see in the center panel here. And while there's lots of new building development in this set of images in China, it's pretty hard to isolate in this visual. And so we've built another model that we call a state model. Think of this as a denoising model, a high level. It's something like a moving average. And this model gives us our best guess at what's actually happening on the ground using all the context that we have. And then we've cleaned up the data set, and you can really see individual buildings pop up as collections of pixels in this state model. And then change detection is simply pixel diffing that state model in a totally naive way. And that's allowed us to get these high resolution and accurate change detection outputs that are what our customers are usually interested in at the end of the day. And that's all I've got. Happy to grab me to find questions around today or shoot me an email at planet.com. And this is just a fun off-nadir imagery in Singapore taken from a different satellite constellation.
Thanks, Hamid, and thanks everybody for having one more, I think, before the coffee break. I wanted to spend a few minutes telling you a little bit about a new project that we are doing for the Gates Foundation. Tetra Tech is a large science and engineering and international development consulting firm. We operate in about 90 countries around the world, and I manage our agriculture and economic growth practice. And for the last few years, the Gates Foundation, as I guess many of you know well, has been investing seriously in digital agriculture, and particularly looking at the role that crop analytics can play in that. And they have heard from many of you and others that ground truth data and training data sets are a major bottleneck to really scaling up the use of crop analytics, especially to support smallholder agriculture. And this project is really designed to help them over the next 18 months design a much larger initiative and set of investments into crop analytics and ground truth data sets. And so we're helping them with that. Because we don't have much time, I think I'll just focus on what we're going to do next, and then look forward to talking and continuing to talk with many of you about where we go with this project. So the basic idea is to do two things. The first is to work with stakeholders in the crop analytics space to identify partnerships, organizational structure, and business models for improving the collection, access, and use of ground truth data for crop analytics, and access to basic insights developed from that data, particularly around field identification, crop type mapping, and yield measurement. Last one being the most difficult. And so we'll spend the next 18 months working to define what that means, but maybe the most useful thing is to explain, I think, the vision that the Gates Foundation has at the end of that process. They intend to invest in a partnership and a host organization or set of organizations for a common ground truth data set structure that can both support public, open uses as well as private sector value addition on top of it. They want to find a way to not just have free and open data for everyone, but deal with some of the issues that others have talked about. So Sherry, for example, showed how useful commercial data collected on mobile phones in India was, but that's a proprietary data set that's not available to everyone. So are there ways that we can work both with the private sector and public sector to create training data sets that everyone can use and get around some of the commercial and public incentive issues that are restricting access to that data at the moment. So that's the first thing the project is going to try and do is work with everyone to come up with a proposed structure for more data collection, sharing, and use. The second component of the project is starting an ag data analytics innovation facility. The facility will start by focusing in India, but later expand to other countries and regions. And the idea is to pick some of the most challenging problems where we can apply new technologies and techniques to deal with the lack of training data sets and invest in partnerships that can help overcome those problems. And to do that around use cases which support smallholder agricultural development. And so we'll be starting scoping out that work next month in India, and over the next year at least have one cycle of experiments in India with multiple partners to try and address some of those problems. So my my request to all of you is, if you have really good ideas about where we should be investing, what problems we should be trying to solve, what use cases are the most important for smallholders, I'd love to hear them, and then look forward to talking to you about kind of the more organizational structural issues around hosting that data and creating a better ecosystem for ground truth data for agriculture. And I'll stop there, and hopefully this will be the shortest lightning presentation to date.